All right, here we go. Graphs. Don't let the empty seats fool you. There's fewer people here now, so there are empty seats. Graphs of logarithmic functions. And actually, this lesson is more than that. It's also an introduction to logarithms. What's a logarithm? Exponent, right. So we're going to learn what exponent, not just any exponent. All right, so if you remember from transformations unit, the graph of the original function and its inverse are blank of each other about the line. So what are they? Reflections about the line, y equals x. Reflections of each other about the line, y equals x. So here's the graph of y equals 2 to the x, and on the right side, the graph of y equals 1/2 to the x. Label it, okay, so this is y equals 2 to the x, this is y is 1/2 to the x. Sort of customary to put parentheses around a base that's, not just a single, like a half, a fraction. Accurately draw the graph of its inverse. Okay, so what we want to do is basically find some points. So here's a nice point, 0, 1. What's the inverse of 0, 1? 1, 0. Here's a nice point, 1, 2. What does that become? 2, 1. Here's a point, 2, 4. What does that become? 4, 2. Here's a point, 3, okay. Not a point, but like you couldn't have extended it to 9, really? Okay, we got what here? Negative 1 and 1/2. So what does that become? 1/2 and negative 1. All right, so, accurately draw, we've got, okay, we know that if it was 9, there would be a 3 here, right? So that would sort of be out there. So we can sketch this. Actually, put it down on that. There we go. And what's happening over here? Well, these guys, as we get really large negative x values, they become very small, right? Tending to 0. So as we tend to 0, we get really large negative y values, right? As the x values tend to 0. And then we could do the same thing here. So 0, 1 becomes 1, 0, right? So the 0, 1 is common. Every exponential function goes through the point 0, 1. Okay, what else do we have? We have negative 1, 2. So that becomes 2, negative 1. We have negative 2, 4. So that becomes negative 2, 4. 4, negative 2. And we would have negative 3, 9, which would be 9, negative 3. So we can kind of fake that point that's being like about here. And now what's happening on the negative side? So we've got negative 1, 2. Oh, we already did that. So we got these positive values here. So this point is 1 and 1/2, right? So when the exponent is 1, we're really just getting the base out, right? Exponent is 1, you get a 2 out. Exponent is 1, you get a half, so that becomes 1/2 and 1. And as these values get smaller, 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 as the x values get larger, the y values get smaller, so then reverse. Right? As the x values get smaller, the y values get larger. There we go, up. And we come down. And I suppose we should label these because we labeled the other ones. So this is x is equal to 1/2 to the y, and this guy is x is equal to 2 to the y, right? Because for the inverse function, we interchange x and y. All right, everybody good with this? State the equation of the inverse and label O. Okay, state it. Okay, so it's x is equal to 2 to the y, and state the equation of the inverse. So this is x is equal to 1/2 to the y. Are the graphs of y equals 2 to the x equals 2 to the y, 1/2 to the x, and x equals 1/2? Are these all functions? Yes, right? There's no repeated y value for an x value. So yes, they are. Right? Where do we reach? The bottom of the left-hand side of the first of 24 pigments. put like 6 sides or something, at least maybe 8.
Oh my god.
I know, right? So just, buckle up.
Those
It's going to be a
forms.
long and bumpy ride.
I don't think we'll get through it all.
Probably not. We've expressed the inverse of y equals 2 to the x and the inverse of y equals 1/2 to the form, in the form x equals. But how can we write these equations in the form y equals? So we know they're functions, right? We look at it and say, hey, that's a function. Function should be written in the form y equals. So to isolate, we must bring the y down from the exponent position. Right? We've got to get rid of the y up here, and somehow it has to come down. We could do this by taking the y root. So if we took the y root, we'd get x to the 1 over y is equal to c, because we'd raised both things, right? So we would go x to the 1 over y equals c to the y to the 1 over y, which would become this, right? Y times, you multiply, or sorry, not multiply, you raise it to the power of the reciprocal, right? That gets rid of the exponent. But that doesn't help because all we've done is move the exponent from here to over there. Still, y is in the exponent. So we need to introduce a new function to perform this operation, the logarithmic function. Let's say that in a bold voice. In the equation x equals 2 to the y, what's the y? It's an exponent. However, we know that a logarithm is what? It's an exponent, right? I mean, that was a little foreshadowing from last week to lead into this. For the equation x equals 2 to the y, we say that 2 raised to the exponent of y has a value of x. We can also say y is the logarithm. So the logarithm is the inverse function, right? It's like squaring and square root. It's like, I write this symbol down for you, I say like this, and you just look at it and go, yeah, sure, perfect, right? I mean, I know these are inverse functions of each other. And then we've got this exponent function, and we're going to throw in the word log, right? Instead of some other weird, so, it would be like some other symbol, like throw in a triangle or something. But no, we use the word log. So we say y is the logarithm to the base 2 of x, which is written like this. Y is equal to log base 2 of x. So that's how you read it. Log or logarithm, base 2 of x. These, these two forms are called the exponential form and the logarithmic form. So x is equal to 2 to the y is equivalent to y is equal to log base 2 of x. Okay, so in other words, when I want to solve for this exponent, so I can write it y equals, this is how we do it. Now, note, the bases are the same. Okay, the 2 is the base in each case, right? It's the base of the exponential function. Now, we've seen the bases of exponential functions, so, we're okay with that. The exponent is y. What's a logarithm? It's an exponent, right? So this y here, it's an exponent. Exponent. And the x, what are we going to say about the x? The x is a number or value. Right? It's the number you get when you take 2 and raise it to the power of y, right? So if y were 3, then x would be 8. Right? And if I had log base 2 of 8, the answer would be, what exponent do you raise the base 2 to? I was like using the base 2, because you say 2, 2. In order to get, which brings in the fine arts, like ballet. Why are there 2, 2? I digress. If y equals 3 to the x, then what's the inverse? X is equal to 3 to the y. So remember, inverse, we're just changing, right? But we want to write that in the form y equals, so what does it become? Log, what's the base? 3, right? So it's easy to say the base is the base, right? If I'm looking at an exponential form, that's the base. This is the exponent. In a log equation, this is what the log thing is equal to, and this is the value you get. So it's log base 3 of x. Okay. So we're going to do a lot of practice of this, but you basically need to be able to translate from exponential form to logarithmic form and from logarithmic form to exponential form. Go back to your graphs in question 1 and label the inverse functions with its equation in logarithmic form. Okay, so we'll go back here. So instead of saying x equals 2 to the y, we say y is equal to log base 2 of x. And here we say y is equal to log, what's the base? 1/2. Throw it in parentheses there, just, make it of x, right? So you put in the x, and you're basically saying the y value is what I would raise 1/2 to get that number, right? So here's how you read this. 1/2 to the power of what will give me x, okay? Or 2 to the power of what will give me x, right? Or x is equal to 2 to 1. Just for some reason we use a word now, right? Log instead of a symbol, right? Like a square root symbol is like, nobody questions it, right? You just learn that back in junior high. Ooh, square root, oh, okay. It's like when you're little, this is the letter A, okay. I'll accept that as a fact. I do not have to discover. There's no discovery learning. I'm going to discover for myself the letter A. Nobody would know how to read, right, as of yet. So they're still working on it. But they're in grade 12. I know, but it takes time. We know you're taking tens of thousands of years of human learning and try to make each human relearn that, right? And it's very efficient. We would never advance beyond where we were 10,000 years ago. Anyways, we now know that, but we'd be good hunters and stuff. We now know that the inverse of the exponential function, why we wouldn't have firearms, so we'd still be using because we wouldn't have invented anything beyond that, right? Yeah, I know, right? It's like we're never going to get through this. We now know that the inverse of y, the inverse of the exponent, okay, you can read that bit, right? So, y equals 6 to the x, inverse, x is equal to 6 to the y. Throw that up, make sure it's... The logarithmic form, okay, the exponent is equal to the log base. What's the base? So if you look at this, the base is 6, right? Log base 6 of what value? X. Okay? So keep doing. The inverse, just interchange x and y, and then write that in logarithm. The exponent f of x, oh my god. We'll have to write that as x equals 10 to the y. You can't write it as x equals 10 to the f of x, right? So you just kind of rewrite this and say, this is y equals 10 to the x. Oh, wow, okay, you're messing me up here. This is like all backwards. So the y must be the exponent, and then that's the base. So this started out as, yeah, f inverse. We can use that because we know the inverse is a function, right? So we're saying, hey, it's a function, right? It's an inverse function. You could just think of this as y equals, right? So the base, right, and then the inverse function was x is equal to, I'm sorry, x is equal to 3/4 to the y. All right, so yeah.
Could you write the logarithmic function as f of x equals something? Is that y equals something?
Yeah. So you can write it as f of x. Here we're writing as f inverse of x because we're saying we started with this function. What's the inverse function? But to just write it as a log function, you say f of x is equal to log base something of some value. In general, for an exponential function y equals c to the x, its inverse can be written as. Yeah, so we start out that way, right? I mean, any function you do the inverse of, you're just going to interchange x and y and then solve for y, right? Now we have a tool to solve for y, right? It's like, I'm going to write this word because that's the tool for solving for y. And then here's my base, and that's what it was equal to. That's the number that I get when I raise the base c to the exponent y. I get the value x, right? So get used to this, these guys interchanging, which I think. All right, so there's a little animated relation of b to the y equals x, which will continue in the background. So that's just this, right? Only they used a b instead of a c. Since all exponential functions have the restriction, right, our base has to be greater than 0 for an exponential function. So the inverses also have the restriction, the base must be greater than 0. So therefore, the inverse of y equals c to the x is y is equal to log base cx, where c is greater than 0. And the inverse of the log works both ways, right? The inverse of this function will be the exponential function, same deal, right? So the base of our log function must be greater than 0. Okay? Base of the log. Since the inverse of the exponential function is also a function, this notation is applicable. F of x equals c to the x is f inverse of x equals log base c of x. And you could also write this. So if the function, if the original function were log c of x, then the inverse function would be c to the x. Right? That's the equivalent of this statement. Right? If your original function is a log function, then your inverse function is exponential. Inverses just undo things, right? The inverse of squaring is square rooting, the inverse of square rooting is squaring. Basic log functions where c is greater than 1. To the right is the graph of y equals 5 to the x. Accurately sketch the graph of y equals log base 5 of x. So we just look for some nice points, right? The nice point on any exponential function is 0, 1. So that'll become 1, 0. The other nice point on any exponential function is when y is equal to 1, you're going to get the base. So if it's 5 to the x, you're going to get the point 1, 5. So the inverse becomes 5, 1. And now if we know the general shape of an exponential, we know that this just goes this way, and this guy comes down, right? This will be 1, negative 1, and 1/5. So at 1/5, so I should probably come in a little tighter. 1/5 will hit negative 1. That should be a little tighter too. And away we go. Okay? So this is the graph of y equals log base 5x. So now it wants you to graph log base 3x and log base 7x on the same grid. So just keep in mind, what would 3 to the x look like? Okay, like, so we know it's got this point here. So let's say we're going to do this guy in red, and we'll do this guy in green. And if you have multicolors, you can do that, or you can do pen, or you can do a dash, you can do something. All right, so every exponential function goes through the point 0, 1, so every logarithmic function must go through the point 1, 0. If it's log 3x, then when x is 1, what do we end up with? 3, right? Because remember, this is the inverse of 3 to the x, right? So, would you like to wrap your car with an advert and make $300 weekly? All right, wait a second. So we had 1, 5 becomes 5, 1. So on the log function, log base 3, be 3, 1. Now what's going to happen at negative 1? What are we going to have? For 3 to the x, remember what we're doing the inverse of. So 3 to the negative 1 is 1/3. How does 1/3 compare to 1/5? Bigger or smaller? Bigger. Bigger, so it's going to be out here. So it's going to be bigger going up that way, right, as we go along, because in order to get to 2, you're going to have to go to 25, right? 25, 2, because the point would have been 2, 25 on 5 to the x. On 3 to the x, it's 2, 9, right? So we're going to hit, at 9, we're going to hit 2, whereas on the purple one, we have to go to 25 to hit 2. So let's label this. Y is equal to log base 3 of x. Okay, and now you get to figure out log base 7 of x. All right, so if we're graphing log base 7 of x, then we think, all right, I'm doing the inverse of 7 to the x. 7 to the x, when x is 1, I'm going to get a 7. I have the point 1, 7. The inverse function, the point will be 7, 1. I have the point -1, 1/7, so I'm going to have 1/7, right? And we're comparing 1/7 to 1/5 to 1/3, so we can see that the green line is going to be lower here, and it's going to be a little more extreme here. You never know when it's on the same sheet or not. To the right is the graph of y equals 1/5 to the x. Accurately sketch the graph of log 1/5, and then graph log 1/3 and log 1/7. Okay, so I'm going to turn you loose. So you work with a couple of points that you can find. So 1 point, well, this is common to all log functions, right? They all go through 0. Sorry, they all go through 1, 0. And then it's like, so for 1/3, just think at -1, that's when you're going to get the value of the base, the reciprocal of the base, right? So I've got -1, 5, -1, or 5, -1, 3, -1, so that the red line, the log 1/3, is going to be below, okay, and the 1/7 will be above. All right, so we're really interested in relative positioning of these guys with kind of 1 point anyways. All right, ready to move? Ready or not? Complete the following statements for the function y equals log base c of x, where c is greater than 0 and c is not equal to 1. So if c is greater than 1, what's the shape of the log graph? So it goes like this, right? As you read from left to right, what's the graph doing? It's going up. We'll call that increasing. Because, words like going up just don't quite capture it. And the graph gets flatter as the value of c. Now we go back and compare here, right? So as the value, what makes it go flatter? Value of c is getting bigger. So the value of c increases. Right? Okay. If c is between 0 and 1, the shape of the graph is, so what's it look like? Doing this. Oops. As you read from left to right, the graph is decreasing, because going down just doesn't cut it. And the graph gets flatter as the value of c, oops, one way. As the value of c, so 1, what do we got here? 1, so flatter is going up this way, so decreasing, right? 1/3, 1/5, 1/7. Decreases. Now we can visualize this. Okay. So here's y equals log base c, where the base is going to be greater than 1. Actually, let's make this 1.1. And we'll watch the graph, right? So as the c value is increasing, as the c value is decreasing, it gets steeper. As the value of c increases, it's getting flatter. The point 1, 0 is invariant. Okay, and then we can pause that and let's readjust. So let's say now we're going to go from 0.1 to 0.9 by 0.1s. And press play.
Still 10.
Yeah.
Oh. Dang, nabbit. 1.1. There we go. Okay, so it's decreasing, it's getting flatter. Increasing, it's getting less flat. So there we go, it's getting flatter. And then, there you go. Complete the table for y equals c to the x. So just your basic exponential function. What's the equation of the asymptote for basic exponential function? Y equals 0. What's the y-intercept? Y-intercept occurs when x is 0, c to the 0 is 1. What's the x-intercept? None. What's the domain? Belongs to the reals, and the range greater than 0. So now y equals log base c of x. This is the inverse function, right? So what's the equation of the asymptote? Yeah, you replace x with y, y. What's the y-intercept? None, same as the x-intercept above. What's the x-intercept? 1. What's the domain? What's the range? Okay. And that information actually matches up with the graph, right? Like we've seen the graphs, and it's like, yeah, okay, it really is true that this stuff, if we look back at just the log graphs that we've drawn, they all have an asymptote of x equals 0. There is no y-intercept. The x-intercept is 1. The domain x has to be greater than 0, strictly greater than. And y, you're covering all values of 1. Graphing a logarithmic function in your calculator using draw in. This is new to me, right? I've never done this. The TI calculator will draw inverse functions. However, they are only drawings, and calculations cannot be made using these drawings. So you can't trace it, you can't do a second calc, etc. But you can graph. To draw the graph of y equals log base 2 of x using the TI calculator, which I now have to get out, and isn't going to work because it's always off by 1 whenever that happens, so I got to reopen it. All right, so start off by graphing y equals 2 to the power of x. Okay, and you can just graph that, right? All right. There's 2 to the x, great. Use second function draw. Second draw. I didn't get second. Second draw. Draw inverse is 8. You can either arrow down there or just press an 8. And we need to say draw the inverse of what? y1, right? Now you can get to y1 going alpha F4 and hit enter. There's other instructions on here. Those of you with older calculators, for whom we all feel very sorry. Sorry you have to use that, but whatever calculator, you need to learn to use whatever calculator you're going to walk into the exam with, right? So if you have the 83, do the y-vars function, enter, enter, and if you have this. Screen should read draw inverse y1, press enter. So when you do that, there's 2 to the x, and here's the inverse. Also in blue, it's amazing. There's the inverse, which looks a lot like if I threw in the line y equals x just for the heck of it, then it would look like, hey, they're reflected above that line. Okay? Remember, this is only a drawing of the inverse. The graph cannot be interrogated. You can torture it as much as you want. Well, it's not going to speak, right? Can't tell you anything. If you want to clear the drawing, go to second function draw and choose clear draw, and it'll clear the drawing. Okay? So drawing is probably just basically taking points. To draw the inverse, it's taking the inverse of those points, but it doesn't know what they are, so all it's doing is I'm just sketching this. I have no idea actually what it's doing. Okay? Oh, you may want to go to zoom square. Zoom 5, zoom square. That just adjusts the aspect ratio so that you're getting a square thing. It's not elongated. This is a little bit longer this way. The screen isn't square, so it's, I don't know what the aspect ratio of that screen is, but second draw inverse. Oh, I didn't say what. Bars, over to y bars, hit enter twice. Okay, so if you want to get y1, alpha F4, it's not on the sheet, but you know that, and there we go. Use the graphs shown to find the value. Okay, so reading off of a graph. If y is equal to log base 2 of 4, okay, so what's our x value? 4, then what's y equal to? then y equals 2. So we could say log base 2 of 4 is equal to 2. If y is equal to log base 2 of 8, so we put in an x value of 8, what do we get out? 3. So log base 2 of 8 is equal to 3. If y is equal to log base 10, that's this graph, of 10, so my x value is 10, what's y? 1. So log base 10 of 10 is equal to? What's a logarithm again? It's an exponent. It's the exponent that you do what? You raise the base 2 in order to get the number. Right? 2 to the 3 is equal to 8. 2 to the 2, etc. If y is equal to log base 10 of 1, then y equals? Y equals 0. So log base 10 of 1 is 0. You have seen log base 2 of 8 equals 3. This means the expression log base 2 of 8 is the exponent. What's a logarithm? An exponent. What exponent? It's the exponent that you raise the base 2 in order to get the number, the value 8. Number or value. I don't know if there's an actual term for that. I've been kind of looking every once in a while, every few years. And sort of, is there an actual, So I just call it the value or the number. So it's the exponent you raise the base 2 in order to get 8. See, I think they still need the word 2, but it should be a word. Complete the following table. Log base 2 of 8. So in exponential form, right, what are we going to say? We're going to say the log base 2 of 8 is equal to something. In exponential form, we go 2 to the power of that something is equal to 8, and that something is equal to 3. Log base 3 of 27 is equal to something. Sometimes we just set it equal to a variable, right? Like y or z or x or a. So this says the base is 3. 3 to some exponent is 27. So 3 to the what gives you 27? 3. This says, what's my base for this guy? 6. So this says 6 to some exponent is equal to 1 over 36. What's that exponent? Negative 2, right? This is 1 over 6 squared, which is 6 to the negative 2. So 6 to the negative 2 is equal to 1 over 36. 16 to the power of something, so 16 to the something is equal to 4. What's the something? 1/2, right? The square root of 16 is 4. The exponent per square root is 1/2. All right? So far, so good. Evaluate each of the following. So here's what I ask myself. I'm doing this. 3 to the what gives me 81? 3 to the 4, right? So you can think this. 3 to the what is equal to 81. That's converting from logarithmic form to exponential form, right? And whether you explicitly write it out or not, you need to be thinking it. So 2 to the what is 128. Zero fingers. 2, 4, 8, 16, 32, 64, 128. 7. Okay, again, this becomes 2 to the what is 128, 7. 2 to the what is 1/32. Negative 5, right? So you just got to say what power of 2 is 32? It's 5, but this is 1 over, so it's negative 5. Okay, 16 to the what is 1/4? Oh, sorry, 16 to the quarter is a quarter? What am I writing? 16 to the what is 1/4? So what's the what? 16 to the what will give you a 4. Let's just do that. 16 to the half will give you a 4, right? But I want 1 over 4, so it's 16 to the negative 1/2, right? So don't try and work out the quarter bit. Just work out the how do I get a 4? Square root, okay, which is half. But wait, the 4's on the bottom. Negative 1/2. Oh, here's the tough one so far. 8 to the what gives you 8? 1. You'd be amazed. Oh, wait, here's the next toughest one. 7 to the power of what gives you 1? 0. This is the toughest one yet. Oh, you laugh, but when you see it written as log base b of b to the x, you'll be sitting, I don't know. Okay? 6. Seriously, you write that log base b to the x, you'll all be sitting there, I don't know. Challenge the challenge question. Log of 4/3, log base 4/3 is 81 over 256. Okay, so you can't just look at that and say what the number is, right? You're probably going to have to do some work to get this, right? So you're going to say, all right, that means 4/3, let's call that x. 4/3 to the x will be equal to 81 over 256, right? So all we've done is say, I'm trying to evaluate log base 4/3 of 81 over 256. I'm just going to set it to some variable. And now I'm going to change it, because you can't just do logs in your head if they're more expansive than log base 3 of 9, which you can do in your head. And you're going to say, all right, that means that 4/3 to the power of x is 81 over 256. At which point you're going to say, now 81 and 256, are they powers of 4 and 3? Well, 81 is a power of 3, right? So what's 81? 3 to the power of 4. And 256 is 4 to the power of? Also 4. So 4, 16, 64, 256. Okay, wait a sec. So that means that I can write this as 4/3 to the x is equal to 3/4 to the power of 4. At which point you can either see the answer right now and say, aha! What's x?
I mean, negative.
Yeah. Negative 4, right? So you can do this. So you say 4/3 to the x is, I got to flip this over. How do I flip that over? I make the exponent negative. Oh, okay. There we go. X is negative 4. Okay. So these guys were both 4th powers of these guys, but not in that order, right? It was flipped over. In general, what's log base c of c? 1. Yeah. So if you're doing the log of the, log base c of c, it's just 1, right? You're saying to yourself, c to the what equals c? 1. What's log base c of 1? Okay, anything to the 0 is equal to 1. What's log base c of c to the x? X, good. So you didn't get 4. Okay, it's important, right? It's sort of, again, you're asking yourself, okay, log base c of c to the x is, what exponent do I raise c to get c to the x? Wait a sec, x, right? Previously, all right, here's the big thing for the day. We saw the equation x equals 2 to the y, blah, blah, blah. Change from exponential form to logarithmic form. Okay, so this is an expression, right, where there's no variables in here. This says 4 to the power of 5 is 1024. So we would say log base, what's the base? Log base 4, what value do you end up with? Of 1024, what exponent do you raise 4 to? Okay, so that's the idea, right? You want to walk out of here today knowing the graphs, but more importantly, if I see 4 to the 5th is 1024, it's log base 4. That's my base. This is the exponent, right? What's a logarithm? It's an exponent. So the exponent has to be after the equal sign, right? The log base 4 of something is equal to 5. What's the something? In this case, 1024. What's the base here? What power do you raise the base 5 to? Okay, so these are the bases. The exponent, right? What's a logarithm? An exponent. So log base 525 is an exponent, right? And it's 2. That's the exponent that we raise the base 5 to get 25. So 5 squared is equal to 25. B equals 2 to the m. M, the exponent, is equal to log, what's the base? Of b. Okay? And again, works backwards, right? If you see this, you say 2 to the power of m is equal to b. You say 1/2 to the power of is equal to? So 1/2 to the power, so put that in brackets, is equal to 26.
Wait,
Doesn't change your answer not putting in brackets. It just makes it less likely to confuse yourself. Projector refresh project. part of this project, we're trying to draw pictures. N to the negative 2 is 1/100th.
Log of n.
So log, what's our base?
100.
No.
And is
What's the base? Base is the thing, if it's an exponential form, the base is the thing underneath the exponent. Okay? What's that equal to? And what's the value? Okay? If I'm looking at it, so seriously, if I look at this, I say n to the negative 2 is 1/100. I can't solve a log. I have to write it in exponential form, then I can solve it. Okay? I mean, unless it's like an obvious value. Use the results from 14. Wait a second. No. 14, the one you haven't. Have we done that? No. Use the graphs shown to find the value of each of the following. Okay, if 2 is equal to log base 3 of x, so 2, that's this 2 here, right? So if 2 is equal to log base 3 of x, then what's x? Let's read it off the graph. What's x? What does this say? 3 to the power of 2 is x, right? That's the... Okay, if 1 is equal to log base 3 of x, okay, that's on this one here, then what's x? If 0, okay, in other words, we'd be given the y values, right? You graph this, that would be y2. So if 0 is equal to log base 7 of x, what's x? So 0, x is equal to 1. Doesn't matter if that's log base 7, or log base 3, or log base 162, or log base 0.15, or log base pi, or log base e. If log 39 is equal to blank, 2, then what's an estimate for log base 3 of 10? So what's log base 3 of 10? That would be here. 2 point. I'm going with 2.1. Okay. But you can go with whatever you want. Okay. It's an estimate, right? The wrong answers are like 17, or 3, or 1.8. Those are wrong answers. Like obviously not. But 2.1, 2.2, it's like, yeah, okay, margin of error, sure. All right, now use the results from 14 to help solve the following equations. So what is this equation that we are trying to solve? How do you write this? Oh, so what's x? That. We should know our powers of 3 up to about 5, right? 3, 9, 27, 81, 243, 729. I don't know what comes next. 2,000 something. What do we do with this? 3 is equal to log 4/5 of x. See, I can't solve this, right? But if I rewrite it in exponential form, if I say, oh, well, that's 4/5 to the power of what? Is equal to x. Okay, so 64 over 125. Okay? So you can't look at log base 3 of x equals 4 and solve that. You have to rewrite it to say x is equal to 3 to the 4th. You have to rewrite this to say what? X plus 2 is equal to what? 3 to the 0. What's 3 to the 0? What's x? Okay, so here's the deal. Here's how you solve logarithmic stuff, right? You say, I can't solve logarithmic stuff, but I'm pretty good at exponents, so I'm just going to rewrite it in exponential form, and then I can work it out. Okay, and by work it out, I mean, you're finding, here we're just finding the value, right? Oh, here, that's a little tougher. We'll get to that one in a second. So what's this guy? There's my base. What's a logarithm? An exponent. It's like one person. I'll throw it out there, otherwise we'll just keep asking. What's the exponent in this case? Negative 4, right? Because that's the log, right? Log base 1/2 of x is some exponent. It's the exponent that you raise the base 1/2 to get x. So what's x? 16. Right? Negative 4, so take the reciprocal of the number inside, 1/2, becomes 2 to the power of 4, which is 16. Okay, what's this one? What's the base?
9.
What's the exponent?
1/3.
So what's x? So it's 1 over 9 to the half, right? Which is 1 over the square root of 9, right? Which is 1/3. Okay, that's the full and gory details. The other one would just be, that's 1/3. Okay, so you don't have to show all of these steps, and I could have put more steps in here, right? You could pretty much go to the answer if it's relatively straightforward. What's this? So the base is x. The exponent, what's a logarithm? An exponent. You might know this by the end of the class. So log base x of 25 is an exponent, right? And it's actually equal to 2. So this says x squared is 25. What's x? X is equal to plus or minus 5, but we know that the base has to be greater than 0, so we're going to show it and then get rid of it. Got to show it. You got to show that you know it, and then you lose it. Okay? Don't lose it, or you'll lose the half mark that goes with showing that you know that it's plus or minus 5, but the base has to be greater than 0, right? So since x is greater than 0, then x is equal to 5. Okay? So show it. Say, hey, I know this is plus or minus, but it can't be negative. So what's this guy? Nope, it's closer to 256. What do you do? Square both sides. So you've got x to the 1/2 squared is equal to 16 squared. So what's x? It's 16 squared, which is 256. Yeah, we're just marching along here pretty good. Okay, what's this guy? Okay, so you've got to be able to translate from the logarithmic form to exponential form and vice versa, right? In this case, we're solving. X to the 2/3 is 16. Okay, how do I solve for a unknown base? You take the reciprocal, right? So you raise it to the power of the reciprocal. And then you do the same thing here. Okay, so this becomes x, and this becomes 64. Right? So it's the square root of 16 cubed, which is 4 cubed, which is 64. Okay? Everybody good? That page so far? So you gotta do a little homework, right? To actually not sit there on the test saying, well, it looked easy in class, but I have no idea what I'm doing. How many have been in that position? Yeah, including me. Yeah, well, should have done a little more work here. Use the log function on the GDC. I've never referred to this as a GDC, but... Okay, look, log. It's so important it has its own button, right? It's at least as important as sine, cos, tan, the inverse, and squaring. So, log 10. Log 10. If you like to, make things nice and neat, you can close off the parentheses. What's log 10? 1. 1. What's log 100? What's log 1,000? What's log of 1/1,000? Negative 3. I'm going to assume you used your calculator for each of those, because some of you worked it out ahead of time. But there's no base on here, right? It doesn't say log base, but what's implied? So what to the power of 1 gives you 10? What to the power of 2 gives you 100? What to the power of 3 gives you 1,000? Let's start with this one. It's 10, right? What's 10 squared? So the implied base is 10. That happens so often that it's called a common logarithm. Okay? So a log base 10 is called a common logarithm, and that's the base that's on your calculator, right? That key is log base 10. So if you don't see a base, what is it? If you don't see a base written underneath the word log, then the base is 10. right? So if you don't see anything in here, what's that? It's a 2. It's a square root. Okay? Now, here's the problem. So if our calculator uses log base 10, how do we work out log base 4 of 16, which we know is what? 2, right? 4 to the what is 16, so we know that that's a 2. Now, use the calculator and type in log 16 divided by log 4, and you get 2. Notice something special? This is equal to 2. All right, well, if we're going to do a little inductive reasoning, we're not going to do it off of one example, right? So, log base 3 of 81. You see that and you think, right, 3 to the what, because I need an exponent, 3 to the power of what gives me 81? You say 4. Use the GDC to evaluate log 81 divided by log 3. And unsurprisingly, we get a blue dot because this thing never works the first time. We get 4. Notice something special again. Here's the special thing. So in general, we can use a graphing calculator to evaluate log base c of b by evaluating what? The log of b over the log of c. The log of the value we want divided by the log of the base. I'd say something, but I think it's at the top of the next page anyways. Oh, no, it's not, but it's right down here. It's called the change of base formula. It's given to you on your formula sheet. That's how important it is. Okay, evaluate without using a graphing calculator. So 2 to the what gives me 512? 2, 4, 8, 16, 13, 6, 4, 1, 2, 2, 6, 5, 12. Okay, 9. 2 to the what gives me 64? 2, 4, 8, 16, 13, 6, 4. What's 9 over 6? 3 halves. Okay. Log base 8 of 512. 8 to the what gives me 512? 8 to the what gives me 64? 2. That one I expect you to know. The 512 one, it's like. Use your graphing calculator to evaluate log 512 divided by. So this was a base 2 log. This was a base 8 log. This is a base 10 log. What's going to happen when we do log 512 divided by log 64? What do you think is going to happen? It's going to be 3 over 2. Well, we convert it to a fraction. 3 over 2, or just say 1.5 is 3 over 2. So, hey, that's 1.5 of 3 over 2. What do you think log base 13 of 512 over log base 13 of 64 is going to give you? 3 over 2. So it doesn't matter what the base is, right? So in general, the log base A of B is equal to log base C of B over log base C of A, where A, B, and C are greater than 0, and log base C of A can't be equal to 0. Okay? If you're doing that, that's a 0, you got problems, right? If you divide them by 0. It's called the change of base formula, as you can change from any base to any other base. Most commonly, we change to base 10, right? And so we noticed that, right? We said, oh, if you do the log of B over the log of A, where these are log, like calculator log, base 10, you get that value, right? Log 512 over log 64. Okay, it's 3 halves. Base change formula on the formula sheet. Evaluate log base 364. So I don't know 3 to the what is 64. Like, I can't do that, right? Like it's somewhere between, well, 3 cubed is 27 and 3 to the 4th is 80. It's somewhere between 3 and 4, right? And log base 3 of 4 is a little bit bigger than 1, but it's smaller than 2. But express this as a single logarithm first. So the question is, can we express this as a single logarithm? So think about this, right? Log base 3 of 64 over log base 3 of 4. If we look at the formula, then we're saying, hey, this guy here is C, right? In the formula, that's C, and in the formula, this is B, and in the formula, this is A. Right? So we got that formula. Here it is back here again. So we have log base 3 of 64, log base 3 of 4. The C's are 3's, but we really have, okay, B is 64, and A is 4. So this really is log base 4 of 64, right? So converting this, okay, we can get rid of the C's, right? So it's equal to log base 4 of 64. And all we've done is said, hey, let's convert that to a base 3 log, right? Then it's log base 3 of the value over log base 3 of the base. Okay? We convert that to a base 10 log. It's log 64 over log 4. As a base 4 log, though, we can evaluate that, right? 4 to the what gives you 64. 4, 16, 64. So this one says, so express as a single logarithm first, right? So that's log base 4 of 64, which is equal to 3. So let's just say this leads to that. Okay, so if we reverse the base change formula and we say it's the log base A of B, it's log base 4 of 64, right? So all you gotta do is pattern match with your formula sheet and then just write it, say, I'm getting rid of the C's, really. Right, and just writing it as log base B of log base A of B based on the formula sheet. Expressing as a quotient of logarithms with a base of 2. So we're writing log base 4 of 64, and we want to convert that to a base 2 log. So it's log base 2 of the value over log base 2 of the base, right? Log base 2 of the value. So base change formula says I want to change from base 4 to base 2. So I write as log base 2 of the value over log base 2 of the base. Now, 64 is 2 to the what? 2 to the 6th. 4 is 2 to the what? 6 over 2 is 3. Expressing it as a quotient of common logarithms. What's common about a logarithm? It's base 10. So this becomes log, and I don't have to write the base now, because if I don't write the base, then what is it? It's a 10. It's assumed to be 10. So it's log 64 over log 4. And you can work that out in your calculator, and you're going to get what? 3. Okay, questions? Base change, right? Your calculator actually, depending on how fancy your calculator is, or actually the firmware version of your calculator, you can do log base, and you choose the base on your calculator. You can put in the base. You can do a log base 464. Nah, let's see if I remember how. So it's alpha F1, no, F2. Here, log base. Okay, so go alpha F2, number 5, log, hey look, you can put the base in, 4 of 64, 3. Okay, if your calculator has the old firmware, we will all shed a tear for you, then you have to go log 64 divided by log 4. You have to convert it to a base 10 log, because you don't have that function in your, or you might, I don't know where, if you do, I don't know where it is. It could be in the catalog. Let's look, second catalog. And I want an L, so if I hit this, there, lin, it might be in your catalog. List, log, log base. So go second function 0, hit the the closed parenthesis here, the L, to get down to the L's, and then arrow down and see if you see log base. And here's the question, do you? No, okay. So if it's not, then you can update your firmware. And if it's an 83, you're hooped, you can't do anything with it. If it's an 84 plus, the firmware can be updated. Okay, doesn't need to be, right? It's not like it's a big deal. Oh, I got to type log 64 instead of over log 4 instead of, where's that function? I don't know where the function is. I think I hit alpha. Meanwhile, you've worked it out and you're moving on, and they're like, it's alpha F1. No. Okay, alpha F3. No. I guess wrong. Alpha F5. No. I don't know where it is. Right? It's like you already evaluated it. Okay, evaluate log base 8 of 32. Without the aid of a calculator, what base would be easiest to do? Base 2, right? They're both powers of 2. So we would say log base 8 of 32 is equal to log base 2 of over log base 2 of. So what goes up top? The value, right? The 32. This is what we want. I want the 32. And what's the base? Log base 2 of the original base? 8. Okay. Log base 2 of 32 is 5. Log base 2 of 2 is 3. And the answer is 5/3. With the aid of a calculator, so if you have the log base, you can use it. Okay? Log base 8, 32, aren't I fancy? You know, and this one, which is math, enter, 5/3, right? Or you just go log 32, because you just change it to a base 10 log, right? Divided by log of the base, which is 8, and you get the same number. Okay? So it's not a big deal if you don't have log base. It's actually probably easier because you won't have anything to forget how to do and then panic about how to do it. And it's like January 25th, I don't remember how to do this. Where's the thing with the... And you're just sitting there saying, this is easy. So 5/3. Well, it's 1.6 repeating, which converts to a fraction of 5/3. Keep going. Evaluate each of the following without the use of a calculator. Okay, what's the base? 10. So 10 to the what gives me 100? 2. 49 to the what gives me 7?
Oh, negative.
Negative? Do you see a fraction there? It can't be negative. 1/2, right? Square root of 49. Right? 49 to the what gives you 7? The square root of 49, which is 49 to the 1/2. 9 to the what gives you 27? So what are you going to do? You're going to go log base 3 of 27 over log base 3 of 9, which is 3 over 2, and you're going to go 3 over 2. Okay? So we're not using a calculator, we're converting to a convenient base. Hey, they're both powers of 3. Okay, log base 1/9 of 27. Same deal. What 3 to the what gives you 27? 3 to the what gives you 1/9? Okay, let's do it this way. 3 to the what gives you 9? 2, so then it's negative 2. So this is negative 3/2. Okay, now you could, of course, do this on your calculator, right? Log 27 divided by log 1/9. That would work. For number 15, we estimated the value of log base 3 to be 10, but what is the value of log base 3 of 10? Or sorry, we estimated the value of log base 3 of 10 to be like 2.1. What is log base 3 of 10? So we go log 10 divided by log 3, and we get 2.0959, so it's 4 decimals, 2.0959. 2.0959. Okay, and here it was approximately 2.1, right? Was it 2.1? Evaluate each of the following without the use with the use of a calculator. Although, like 10 to the what is 80. So 10 to the 1 is 10. 10 squared is 2 is 100. So it's bigger than 1, smaller than 2, closer to 2. Okay, so what does it work out to? What are we doing to the nearest what? Nearest 10. So what's log 80? 1.9. Okay, so you shouldn't be surprised, right? You say, well, it's between 1 and 2. And here, a quarter, log base 30 of a quarter. So what do we do? Log 30 divided by log 1/4. Negative 2.5. Graphing a log function on your calculator using y equals. Earlier we looked at the graph of y equals log 2 to the x by graphing, log base 2 of x. Y equals 2 to the x of doing the draw inverse, but we cannot interrogate this. your calculator does not allow you to enter a base of 2 for a logarithmic function, classic mode, older calculator, right? You cannot do a log base 2. Then what are you going to enter to get this? Yeah, log of x over log of 2. Right? You're just going to use the base change formula to change to a base of 10, because that's what your calculator can graph. If you have the log base function, you can just do that, right? Are we done? Like, that's amazing.
Yeah, now this is for me.
That's amazing.